Clustering is a form of unsupervised learning, used to group similar observations together in such a way that the observations in a cluster are more similar to one another than they are to observations in another cluster. More formally, we aim to minimize the intracluster or within-cluster variance, which we denote WSS for within sums of squares. There are many different clustering algorithms, but we'll focus on two of the most popular, k-means and hierarchical clustering. Before we go any further, it's important to note that clustering is a product of many different fields, which means that there's a lot of different terminology to represent the same ideas. First, we'll talk about k-means, which is also known as the LBG algorithm, or as the generalized Lloyd algorithm. If we have a data set that contains n observations and p variables, and we want to create k clusters, then the k-means algorithm is as follows. Step 1. Randomly select k observations. These k observations will be called the cluster centroids. Other terms that may be used for this concept include centers, vector quantifiers, or VQs, codewords, and codebook vectors. Step 2. Compute the Euclidean distance from every observation to each of the k cluster centroids. Step 3. For each observation, assign it to the cluster that it's closest to. Step 4. For each of the k clusters, update the cluster centroid by computing the mean of all observations in that cluster. This will result in a p-dimensional vector. Step 5. Iterate until you reach your stopping criteria. This will either be some maximum number of observations or a level of tolerance, such as stopping when the cluster centroids no longer appear to move. In R, you can use the k-means function to perform the k-means clustering algorithm. The first argument is the data set that you'd like to perform clustering on. The second argument is the value of k you'd like to use, which is the number of clusters you'll end up with. And then you can pass your stopping criteria, such as the maximum number of iterations. It's important to note that, due to the random nature of the first step of the k-means algorithm, the only way to ensure reproducibility is to set a seed first. In R, you need to use the set.seed function before running the k-means function. The k-means function returns a number of things, and I encourage you to type $k-means into the R console to read the documentation for the function. The returned components that are likely of the most interest are the cluster element and the within SS element. The cluster element is a vector of length n, letting you know the cluster assignment for each of the n observations. The within SS element gives the within sums of squares for each of the k clusters. You can also access the total within SS through the tot.withinSS element. So how do we choose the value of k? Well, we'll vary the value of k and then see what happens. There are a handful of ways to do this, but we'll focus on checking the total within sums of squares and the Davies-Bouldin index. Once we've varied the value of k, we can create a plot with the value of k along the x-axis and the total within SS along the y-axis. Then, we look for the value of k for which there is no longer meaningful improvement or meaningful decrease in the total within SS. We need to be careful with this though. If we simply pick the value of k that results in the lowest total within SS, we might have far too many clusters, or we might even end up with every single observation being its own cluster. To prevent this, we can use the Davies-Bouldin index, which penalizes overfitting. It's also important to note that the k-means algorithm is very sensitive to the initial observations that are chosen as cluster centroids. Therefore, for the best results, we should repeat the k-means algorithm many times and aggregate our results in some way, such as by taking the mode of the assigned cluster. Be careful with this as well, though, because there's no guarantee that the cluster labels will be the same when we start with different cluster centroids. We'll see this in the R example later. This also applies to picking the optimal value of k. We should repeat the previously described procedures multiple times in order to pick the optimal value of k. Hierarchical clustering is the other extremely popular clustering technique. With k-means, we needed to know the number of clusters that we wanted to end up with at the very start when we initially used the k-means function. This is not the case for hierarchical clustering, which is one of its many benefits. We can perform the hierarchical clustering first and then decide the number of clusters afterwards. There are two types of hierarchical clustering: divisive and agglomerative. With divisive, you start with every single observation being one cluster, and then you iteratively split the most heterogeneous cluster into two until you have every observation in its own cluster. With agglomerative hierarchical clustering, the opposite is true. You start with n clusters, and then, at each step, you combine the two most homogeneous clusters into one. We will focus on agglomerative hierarchical clustering, which is what's implemented in the hclust function in R. The algorithm for agglomerative hierarchical clustering is as follows. Step 1. Compute the distance matrix for your dataset. Step 2. Make every observation its own cluster. Step 3. Combine the two most similar clusters, as determined by the distance matrix, into a new cluster. Now, there should be one less cluster than in the previous step. Step 4. Update the distance matrix by computing the pairwise distances between each cluster. There are many ways to define the distance between two clusters, and I encourage you to type $hclust into the R console to see the full list of available linkage methods. Some examples include single linkage, complete linkage, and average linkage. Step 5. Repeat this process until all observations have been combined into one cluster. As an example, let's say we have 5 types of candies that we'd like to cluster: peanut butter cups, a cookies and cream bar, red licorice, sour keys, and sour gummy worms. Naturally, our intuition tells us that the chocolates are similar to one another, as are the sour candies, and that the sour candies are probably more similar to one another than the peanut butter cups are to the cookies and cream bar. Red licorice is probably more similar to the sour candies than it is to the chocolates, but probably isn't as similar to the candies as the chocolates are to one another. Let's draw what the dendrogram might look like for this scenario, following the algorithm for agglomerative hierarchical clustering. First, each candy is its own cluster, so we have a total of n equals 5 clusters. Next, we combine the two most similar candies into one cluster, which are the sour keys and the sour gummy worms. Now, we've got n minus 1 equals 4 clusters. We now move on to the next iteration of our algorithm, and we again look for the two clusters that are the most similar to one another. In this case, that's going to be the peanut butter cups and the cookies and cream bar, since they're both chocolates. We combine those into one cluster, which leaves us with n minus 2 equals 3 clusters. For the next iteration, we again combine the two most similar clusters. Since licorice is more similar to the sour candies than it is to the chocolates, we combine these two clusters into one, which gives us n minus 3 equals 2 clusters. On the very last iteration, we again combine the two most similar clusters into one, which in this case leaves us with just one cluster overall. We've now finished the agglomerative hierarchical clustering algorithm, and here we have a completed dendrogram. From here, we can decide how many clusters we want, using any of the techniques discussed previously in the k-means section of this video. Let's say, for example, we wanted to pick 2 clusters. To determine the cluster labels, we simply draw a horizontal line at the location on the dendrogram where our line will create 2 broken links, which is here. We can see that our first cluster contains the chocolates, and our second cluster contains the candies. If we instead want to pick 3 clusters, we can draw a horizontal line here to create 3 broken links. Our 3 clusters would then be the chocolates, the licorice, and the sour candies. Now, you may have also noticed when I drew the dendrogram that I drew the lengths of the lines unevenly. This was intentional. The length of the lines represent how similar the 2 clusters are at the time of the merging. We can see that because the length of the lines between the sour keys and the sour gummy worms is very short, these 2 clusters were very similar when they were merged together. On the other hand, when we joined the sour candy cluster with the licorice cluster, these 2 clusters were not very similar, which is indicated by the longer length of these lines. What if we wanted to visualize the cluster labels themselves? Of course, we can use base R for this, but we can use the factoextra package to create plots that are a bit more visually appealing. We're going to perform agglomerative hierarchical clustering on the iris dataset built into base R. To do that, we're first going to need to compute the distance matrix using the Euclidean's distance metric. Now, we're only going to be able to use numeric variables for the distance matrix, so I'm going to exclude the 5th column, which is the species column. Next, we're going to use the hclust function, and we're going to pass the distance matrix that we just created, as well as the linkage method that we'd like to use. Here, I'll use complete linkage. Next, I'm going to plot the dendrogram for the hcomplete object that we just created. To do this, we can use the plot function directly on that object. I'm also going to use the rect.hclust function to create 3 rectangles displaying what the cluster labels would be if we picked 3 clusters. In this case, I'm picking 3 because there are 3 species in the iris dataset. Next, I'm going to load the dendextend package. The dendrogram that we have here looks alright, but we can make it look a little bit better with the use of an external package. Now, we'll convert the hcomplete object that we created earlier using the hclust function to a dendrogram object using the as.dendrogram function. Next, I'm going to use the color branches function from the dendextend package to plot a dendrogram that looks a little bit better than the one that was created directly using the hcomplete object that we created using the hclust function. I'm still going to use 3 clusters. This plot is a little bit easier to read than the one we had previously. Now I'm going to paste in the k-means code that we used earlier. Next, I'll load the factoextra package, which will help us visualize the clusters for the 2 different algorithms. Now I'll use the fviz_cluster function from the factoextra package to plot the cluster labels. The first argument that I'm going to pass is going to be a list. This list should contain the data that I originally started with, which was the iris dataset in our case. It should also contain the cluster labels for the algorithm that we chose. So to get the cluster labels for the agglomerative hierarchical clustering, we're going to use the function cutree on our hcomplete object. And we also need to specify the number of clusters. Next, we need to tell the fviz_cluster function which variables we'd like to plot. Because we have a multivariate dataset, and we can only plot in 2D, we need to pick which 2 variables we'd like to use. To keep things simple, I'm just going to use the first and second variables, which if we check the call names of the iris dataset, we can see is going to be sepal length and sepal width. I'm also going to specify a few additional arguments. I'm also going to suppress the legend, since the cluster labels 1, 2, and 3 are not going to be very meaningful. Next, I'm going to copy and paste this same code, and instead I'm going to pass the k-means clustering. I need to change the cluster labels. So to get the cluster labels for a k-means object, you type the name of the object and then you can use the $sign operator and you want to select the cluster element. I should also, of course, change the title since this one is using k-means. Finally, I'm going to copy and paste this one more time, but this time the cluster labels are going to be given by the species column of the iris data frame. I will also change the title. Next, I'm going to run all 3 of these so that we can compare the results. Here we can see the 3 clusters created for the agglomerative hierarchical clustering with the complete linkage. We have sepal.length along the x-axis and sepal.width along the y-axis, which was determined by the choose.vars argument in the fviz_cluster function. Sepal.length was the first column in the iris dataset, and sepal.width was the second column in the iris dataset. Next, let's take a look at the k-means results. Here we can see that the clusters are fairly similar, but there is a bit of difference. In particular, these 2 clusters here seem to be different between the 2 different methods. We can also see that the colors of the clusters are not the same. So here, the top left was green for k-means, but it was red for agglomerative hierarchical clustering. This is something that you need to be really careful about because when you use a different algorithm, there's no guarantee that you're going to get the same labels to represent the same cluster. And finally, here we can see the true species label. So if we compare the 2 clustering algorithms, we can see that both clustering algorithms did a really good job at identifying the cluster in the top left, but not as good of a job with the other 2 clusters. You should also play around with the choose.vars argument and see what this looks like with different sets of variables, because we can see that there's not a lot of separation between these 2 clusters along these 2 axes, but that might not be the case along every pairwise combination of axes. You might be wondering why we might choose k-means over agglomerative hierarchical clustering or vice versa. The large benefit of choosing hierarchical clustering is that we don't have to pick the number of clusters ahead of time, and we can play around with this value without having to rerun the entire algorithm. With this, though, comes some serious computational costs. Hierarchical clustering is much more computationally expensive than k-means, and therefore k-means works more quickly for very large datasets. Dendrograms also become quite difficult to interpret as you increase the number of observations in your data. Another benefit of using hierarchical clustering is that you have more freedom in how you want to define similarity, whereas with k-means, you're restricted to using Euclidean distances.